As it revolves around the sun, the Earth receives life-giving energy. Without this energy, life as we know it would cease to exist. Yet the sun is only one star in a galaxy of 100 million stars, known as the Milky Way. Millions more galaxies exist beyond the Milky Way. Here, the Great Nebula, in the constellation Andromeda, where countless millions of stars are arranged in spirals. These stars are so distant that light from them, traveling at 300,000 kilometers per second, takes 2.5 million years to reach us. Our sun is simply a star which is relatively near to us. That's why it appears bigger. For us, the sun is the most vital of the heavenly bodies. We all enjoy the sun's warmth, particularly during a seaside holiday. Some bathers realize that the sun's rays can be beneficial to their health, provided that measures are taken to prevent overexposure. The sun's heat and light come from the fusion of hydrogen atoms to make helium atoms. This dynamic condition, resulting in a great ball of white-hot matter, has been in existence for thousands of millions of years. The sun's outer surface, or photosphere, has a temperature of almost 6,000 degrees Celsius. The beauty of the sun's outer atmosphere, or corona, can be observed during an eclipse of the sun. The corona extends some 5,000 kilometers out beyond the photosphere. At its center, the sun's temperature is about 10 million degrees Celsius. The sun's energy is generated at its center. However, only a fraction of this energy reaches the Earth. But like a slow-charging battery, the Earth has stored this vital energy since before man. Some 300 million years ago, trees of the great primeval forests were drawing in the sun's energy through their leaves and building it into the substance of their timber. As each generation of forest trees was replaced over countless centuries, so the decaying remains were crushed under layers of rock, sand, and other strata. This massive pressure eventually turned the remains into fossil fuels. Marine life also draws life-giving energy from the sun. Fossil fuels are also derived from the dead marine life of long ago. One of these fuels, natural gas, is the substance of prehistoric marine plants and animals transformed by heat and pressure over millions of years. Today, the massive investments in offshore gas fields allow us to utilize this vital resource, so meeting Britain's growing demand for energy. So from the sunshine of millions of years ago, we get one of the most commonly used fuels of today, natural gas, which is essentially methane. The greatest benefit we draw from the sun is its power to grow food. Food is a form of stored sunshine. We can consume it directly without having to wait millions of years. So the food we eat and the way in which it is prepared for consumption depends upon the sun. This biscuit baking process is but one example of how natural gas, a product of the sun from long ago, is used in a modern industrial plant. We could not breathe without the sun, for there would be no greenery to provide essential life-giving oxygen in the atmosphere. Our fuel, food, the air we breathe, are all benefits provided by the sun's energy. The pattern of our lives is dictated by the sun and depends on which part of the Earth's surface we live. For example, we are all familiar with the changing scene brought about by the change in seasons. 4 seasons are determined by the relative position of the Earth to the Sun. How do these seasons come about? And why is it that summertime in Britain is wintertime in Australia? Well, let's consider the seasons of the Earth's northern hemisphere. Throughout the year, the Earth moves around the Sun, while simultaneously rotating on its own axis. We can imagine this axis as a spindle passing through the poles. The Earth takes 24 hours to complete one rotation, during which Britain is part of the time in the Sun's light, and part in darkness. In other words, day and night. But there is another consideration. The Earth's axis is tilted. Here the Earth is stopped in the December position, midwinter in the northern hemisphere, with the North Pole tilted away from the Sun. This tilt, which is about 23.5 degrees, means that Britain, being in the northern hemisphere, has longer nights than days. The effect of this is familiar to us all. The landscape in Britain changes because of the short winter days, which are due to the Earth's northern hemisphere being tilted away from the Sun. However, if we look at the model again, we see the tilt also results in the British Isles receiving the Sun's rays at a small angle to the Earth's surface. Therefore, Britain receives less direct heat. Because the Earth is round, the equatorial regions receive the Sun's rays at a much larger angle, and therefore get more direct heat from the Sun. So, quite apart from the Earth's tilt, the nearer we are to the equator, the hotter it is. From winter, the Earth moves on toward the spring position, resulting in a change of scene in Britain. By the end of March, the Earth is in this position, the spring equinox. The Earth's axis is at right angles to the Sun's rays. If we look at the Earth from a celestial position above the northern hemisphere, we can see that Britain spends the same time in darkness as in daylight. This is the spring equinox, the days being the same duration as the nights. The year progresses, and the Earth reaches the June position, midsummer in the northern hemisphere. Because the Earth, while spinning, behaves like a gyroscope, its axis maintains its original preferred direction. This means that because the Earth has moved to the other side of the Sun, the North Pole is tilted toward the Sun and not away from it. Britain has longer days, shorter nights, making Britain warmer. While the Earth is in this attitude, Britain faces the Sun more directly than in winter. Britain receives more direct heat from the Sun. This is because the Sun's rays are striking Britain at a larger angle in summer than in winter. A third reason why our summers are warmer is that this light has a shorter distance to travel through the Earth's atmosphere to reach Britain. Weeks and months pass, and the Earth moves on to the autumn position. Here, as in spring, the Earth's axis is at right angles to the Sun's rays. This is the autumnal equinox. Autumn brings the beautiful gold and brown colours which are so familiar to us. Nature's final burst of glory before winter sets in. The year draws to an end. The Earth is back in the December position. Winter in Britain in the northern hemisphere, and summer in Australia in the southern hemisphere. Now you can see why. So the sun dictates our seasons, as the Earth moves around it throughout the year. The sun is vital to our very existence on planet Earth. The sun, our benefactor.
In this program, we're going to look at collisions and analyze the parts which energy, force, and momentum play in them. Space gives us a rare opportunity to study objects free from the effects of friction. A body in space will keep its velocity until it collides with another body. An object won't change its velocity until a collision applies an outside force to it. Unless something is stopped, it'll drift along forever. It would take quite a collision to stop the Earth or change the course of the Moon. When a meteorite collides with the Moon, its kinetic energy causes it to blast out a crater. Much of the kinetic energy is turned to heat, melting the rocks to liquid. We can get a good idea of what happens during an impact by looking at a drop falling into a cup of milk. If you look closely at moon craters, you can sometimes see a peak in the middle. On Earth, we're protected from most meteorites by the atmosphere. Most of their energy is dissipated as heat through friction with the atmosphere. Sometimes an extra large meteorite gets through and blasts a crater, such as here at Wolf Crater. It's 700 meters across, similar to a moon crater. However, it's 3/4 full of sand and the walls have been partly eroded. When the trampolinist hits the trampoline, most of his kinetic energy is returned to him as he springs back up again. This is known as an elastic collision. An elastic collision is one where all the kinetic energy before the collision is returned as kinetic energy after it. None is lost as heat. In practice, this never quite happens, except in collisions of subatomic particles, but we can get pretty close. All ball games depend on elastic collisions to varying degrees of efficiency. The club slows down when it hits, losing kinetic energy. Up to 80% of this energy is kept as kinetic energy as the ball springs away. Only 20% is lost as heat. A tennis ball is only about 50% efficient, and a squash ball as little as 10%. The energy that isn't transferred to the ball is dissipated as heat. When a player hits a ball, energy is transferred from her muscles to the swing of the racket, then through its strings to the ball itself. In each part of this process, some of the energy is converted to heat. When a skateboarder skates down one side and back up the other, He's making a near elastic collision with the earth. The friction losses have to be made up by working with the legs. However, once he falls off, the collision is no longer elastic. There is friction. Sometimes kinetic energy is deliberately converted into heat. For example, when we want to stop this plane in a very short distance, we're going to have to dissipate energy very quickly. The arrestor hook dragging on the ground gives some idea of the heat that will be generated. The tyres touch and some of the rubber is vaporized. Due to the restraints of friction, tyres can't slow a vehicle much faster than 1 G. However, most of the energy is absorbed by a wire cable pulling against a large pair of disc brakes. Pads grip the disc and generate heat by friction. The plane's energy goes up in smoke. Even if the rubber could have held such a sudden stop, it's doubtful if the plane would still fly as well with brakes big enough to do the job. When space capsules return to Earth, they too use friction to dissipate their kinetic energy through friction with the air. The outside heat shield vaporizes or ablates, carrying away the heat. When a car hits a wall, its kinetic energy must also go somewhere. When the front of a car crumples, energy is absorbed. The more it crumples, the more energy is absorbed. Safety engineers design cars to crumple evenly in a crash. They choose which members will crumple and how much. The advantage of crumpling over an elastic collision is that the stopping force is even. It doesn't increase with distance. The idea is to have the bonnet crumple and the passenger compartment remain rigid. By looking at high-speed film of a collision, engineers can see exactly where cars buckle. It's all very well for the front or rear end to crush, but if a car is hit side on, the passengers will become part of the energy absorption process. This is a top shot of a car hitting a normal power pole. The energy-absorbing crumpling process intrudes right into the cabin. This is an experiment with a power pole that crumples to absorb some of the energy. The crushing is evenly matched between the car and the pole. A top shot shows the honeycomb behind the pole being crushed. The pole hardly intrudes into the cabin at all. The lesson here is to try to avoid hitting a normal pole side on. Truck cabins don't have much spare metal to crumple. They're very rigid as they're designed to withstand a full load hitting from behind. But although a truck cabin is designed to withstand the large forces involved in a sudden stop, a human is not. If we can slide to a stop, the forces are minimal. If you stop in 1/100th of the distance you fell, then the stopping force is 101 times your weight. We use the force generated by a sudden stop in hammering. A trampoline is designed to give a long stopping distance. Similarly, grass gives a softer collision than a hard surface where the change of velocity is sudden. The momentary force on the joints and bones of the leg can be extremely large. In order to reduce jarring force, modern running shoes are designed to reduce the force of impact on the feet and legs by increasing the distance over which your heel stops. Shoes are made with a padded rubber sole that acts rather like a mini trampoline. When the feet hit the ground, the foam rubber compresses. and the feet are slowed down over an extra few millimeters. In this test, a section of an aircraft fuselage is dropped to see the effect on the safety of the passengers. If the aircraft shell had been rigid,